let's start kind of at the beginning here. And I intend to return to this subject quite a bit. I just tried to test a little bit to see what you guys probably knew. And some of you I know have had a course in physics before. So you have perhaps more information here, or at least a recollection of things from prior discussions, like some of these might ring a bell as forms of potential energy. Whatever it is that you learned when it came to potential energy, it will probably work out just fine today. But there's probably some things we're going to talk about that you did not discuss in your prior discussions of potential energy that we need to kind of bring to fruition here. Because the truth is, potential energy is energy of an interaction. An object doesn't have potential energy. An object interacting through a conservative force can store potential energy. This is not something about the object. This is something about an interaction between the object and something else. I've said it twice. So when we talked about kinetic energy, we are speaking about an object, but potential energy is something an object has because of its interaction with something else. That's why it's different. An object by itself cannot have potential energy. An object interacting with another object or something else can. So all forms of potential energy involve an interaction. Many forms of potential energy involve one of the fundamental forces. Now, for our purposes here, our forms of potential energy will involve what are called conservative forces. I've struggled to find a good way to define conservative forces with students, so I generally don't, because the only definition I can give are definitions that have circular logic to them. The best thing I want you to understand about conservative forces, something that will serve us better in the future, is that conservative forces are path independent. That will be important later. Conservative forces are path independent. So I'm going to start this conversation a little different than I did first period, because my conversation about this in first period did not go over as well as I'd like. It wasn't terrible, but I felt like it was a little bit wonky. So I'm going to start somewhere else. You tend to do better if I give you something concrete. So let's start with something that's a little bit concrete. We'll go back to the inclined plane. It's simple enough. And it'll give us enough of a concrete example. So, say 30 degrees, let's say the whole thing is 10 meters. Okay? How much work is done in taking our object and moving it this way to the top of this ramp? I'm just going to lift it straight up. How much work is done doing that? You'll need a mass here. So let's say the object has a mass of 2 kilograms. Now, in doing this problem, you're probably faced with, well, what do I use for how much force is required to lift the object? Well, anything over 20 newtons will do it, right? It's a 2 kilogram box, so it has a weight of 20 newtons. I have to apply a force at least equal to 20 newtons. So let me be very clear about what I want. I want the least amount of work done in lifting the box to the top of the ramp. And if you use your calculator, I'll be disappointed in you. Not because you can't use a calculator, but there's no reason to. Take a minute and calculate how much work is done in lifting this object to the top of the ramp. I'll pick one in a minute. So it's clearly work is force times distance times, well, let's not use that. Force times change in position times the cosine of the angle. I'm lifting up the rock. How much force do I have to apply to lift the rock? 20 newtons. I want to lift the rock, I need to apply 20 newtons. 20 newtons of force. How far am I going to lift the rock? Well, I need to know this height. I have a triangle there. Hypotenuse is 10. Angle is 30 degrees. Sine of 30 is a half. That has to equal the opposite side divided by 10. So the opposite side is 5 meters. The fact that some of you are stumped about how high it is bothers me a lot. I drew a very clear triangle with angle and hypotenuse. And I push up on the rock, and the rock goes up, so cosine 0 degrees. Wasn't a whole lot to do here, was there? So this is the work done by me on the rock. I'm going to be very careful about how I write this. The work done by me on the rock is 100 joules. How much work was done by gravity? While I was lifting the rock, how much work was done by gravity? Not a hard question. Negative 100, that's right. Gravity was pulling down the whole time. But the rock was going up, so gravity did negative 100 joules of energy on the rock. 100 joules of work on the rock. All right, so the rock is here now. I did work against gravity to get the rock up there. The total work done was 0. So the rock is now up here, but has 0 velocity, no change in kinetic energy. Everybody follow that okay? So I applied just enough force to get it there. Now, look, some of you are going to be confused by that statement. A little extra force was required to get it to start moving, and a little less force was required to get it to stop moving. Stop worrying about the beginning and end of this problem. If I stop lifting it, it stops moving. Unless I drop it, and then gravity does work bringing it back down. Fair enough? All right. If this surface is frictionless, how much work is done by gravity bringing it back down? Now, it's going down the ramp. So show me what you would do to figure out that amount of work. That displacement's 10, stuff like that. That's the one that's doing the work, bringing the rock back down. Then our work by gravity, and I'm only doing this to be nice because there's some of you who don't know why this is true, and I am bothered by it. So I'm being nice and I'm being deliberate and slow. That's going to end here in a minute. But it's going to be the force of gravity times the displacement times the cosine of the angle. So looking at that, the rock, there's a force this way. The displacement is that way. So I'm thinking the force is the weight of the rock, 20 newtons. The displacement, 10 meters. Cosine, 60 degrees. Right, that's got to be this angle, and that angle is 60 degrees. That's still 100. First, that's the idea of the path independence of a conservative force. Did you notice that clearly? Even though it went this path, because it's under the action of a conservative force, the same amount of work is done. Now, I can't prove this to you this moment, but it's not about the sideways motion of the object. It's about the absolute change against gravity. And the only portion was against gravity was when it was changing its height. That's why we get the same amount of work coming back down as we did going up. But there's something else more important here. And I think anybody who's paying even a small, reasonable amount of attention will be able to figure this out. That if I had a different ramp, say one that was twice as high. So this is 10 meters this way. That placing a rock here would require more energy. Does that make sense? I'm using the same amount of force, but because I'm going twice as high, it would take 200 joules of energy to get it up there, right? Twice the displacement. And even not knowing what this length is down the ramp, Probably going to get 200 joules of energy back on its way down. It's clear to me that there's something important about being lifted higher, that somehow that grants the rock more possibility of having faster kinetic energy when it slides down the ramp. Nobody's been to a water park, hasn't looked at the big slide going, I want to go down that one. And knowing in their head why you want to go down that one. You're going to be faster at the bottom. This idea that there's something special about being lifted up higher was not something that was lost on people who were looking at work in this way. So they wanted to name something about this difference, about the object at these different positions. There's something important about these positions. Now, there's nothing inherently energy related to being at the top of this ramp versus the top of this ramp. But we all know it takes more work to get to a higher location. We know that just by the simple definition of work, and probably from our own experience. You take the elevator if it's any flight that's too high. I don't want to climb all those stairs. It's a lot of work. Well, we know those kinds of things. Now, I'm bringing this to your attention because once I place the ball up there, I can release it any time in the future, and gravity will do the work to bring it back down. This is the concept of potential energy, that energy is stored. It's not stored with the object. It's stored in the interaction between that object and some conservative force. In this case, it's the interaction between the rock and the earth. And we name this interaction potential energy. Potential energy is not like kinetic energy. Potential energy is a construct. We, as humans, have constructed potential energy as a means of tracking the work done by moving an object. I'll say that again because it's important for you to understand that this is something we created. I'm not sure the universe is filled with potential energies. I think we as humans have constructed this idea as a means of dealing with the flow of energy. Potential energy is the interaction between two or more objects through a conservative force. In large measure, it's about position. Now, this is a definition. It's not like other things where it's a theory or it's a law. Potential energy is defined. And so let me help you with the way we're going to define potential energy because it seems a little weird. First, for our purposes in this class, potential energy requires a conservative force. So there's only going to be a small number of potential energies in this class. In fact, 3 total. So we'll deal with what we just saw here, gravitational potential energy. We're going to deal with elastic potential energy, and there will be another form of elastic potential energy second semester when we deal with torsion and torque. But generally, 3 forms of potential energy in this class. There are other forms of potential energy in nature, and many of them, actually. There's lots of ways to store energy in this way through an interaction. But for us, we're going to focus on these. The definition of potential energy is this. First, we're going to use an uppercase U as the symbol for potential energy. Uppercase U. So if I write U with a subscript G, I'm talking about gravitational potential energy. And if I have U with a subscript E, I'm talking about elastic potential energy. We'll talk about both. Now, this part is the crux. This is important. Work done by a conservative force equals minus the change in potential energy. Work done by a conservative force equals minus the change in potential energy. Often I will write this as delta U equals minus the work done. This is a definition. three-line equal sign is definition. We define the change in potential energy as minus the work done by a conservative force. All of those things are required for this definition, but it is a definition. Look, I have not defined hardly anything in this class before. We've used words, we have a lot of mathematical relationships, but this is a definition, it's a construct that we have. But this is how we will define potential energy. So whenever we're faced with the opportunity to find work done by a conservative force, this is how we'll define it. Now, I'm trying to say this to you with some future thoughts in mind. There are lots of conservative forces out there, and AP Central is very aware of that. They could come up with some force that is a conservative force, and they could put some function here. And any kind of function they put here, if they tell you it's a conservative force, suddenly you'll have to probably find how much work is done in using that conservative force, and therefore how much energy is stored. This is that 40% I was talking about. It's important that you understand that we've defined work in a very specific way. So we are now defining potential energy in a very specific way. It's unlikely that this will come up, but it has happened where they've given us some interesting function. Usually it's something like a non-linear spring. That's the most likely place this will show up. When we did our lab before Thanksgiving, we used a linear spring, F equals Kx. There are lots of springs that don't follow that. They're called non-linear springs. In fact, the most likely problem on the exam, this has come up as a non-linear spring. One where the spring's force goes up by the cube of the position. It's a non-linear spring. And it's conservative. And yeah, they exist in the world. We make them. There's lots of materials like this. Things that get much more force for smaller displacements. So just be aware that I'm trying to look at the future of this. But for the present, I don't have to worry too much about the hard math. I do need you to understand that that negative sign is important. And here's why. I want you to consider what we just did. We took a rock and we lifted it to some new place in space. The work done by gravity required that we knew the mass of the rock, we had an understanding of how high the object was lifted, and recognized that the force that we were working against was gravity. So when we calculated the work done by gravity, we said mg was the force of gravity acting on the rock. The displacement was h, and we were aware that gravity was pulling down, but the rock was moving up. And this was how much work was done by gravity. This gave us negative mgh. And yeah, that was 100 joules, but for right now, that's negative mgh. That also means that this is minus the change in potential energy. Well, let's think about that for a minute. If I was to solve this for potential energy, mgh would be the change in potential energy. Perhaps it might be better to say mg h minus h naught, where this represents the change in height. Think of it this way. Box on the ground, lift it up here to the table. That's one change in height. Lift it up to the top of this table, another change in height. Each one of those has been work done against gravity, lifting the box higher and higher. It's path independent, which means it doesn't matter that I lifted it from over there and placed it here. The change in potential energy is just about the change in height. That's all I have to worry about. Remember that the ramp, it didn't matter that it went up the long side of the ramp or goes up the short side of the ramp. The change in height is all that determined how much the energy changed. And I say that consider it's h minus h naught because the amount of work started in one place and ended someplace else. That was a different amount of work than going from here to here. So delta H makes sense, right? Now, the problem with our concept of potential energy, and I say problem because it can lead to some issues with us, is that this definition for potential energy is great, except it's based on an assumed reference level. H naught represents the reference level, where the object was before you did the work. And this H represents where it is after you did the work. So when we define this as potential energy, we need to be careful about what we call the reference level. For example, this is useful because of the example we started with. In that example, we moved the ball to the top of the ramp, let the ball go, it rolled down the ramp. It was useful because it allowed us to convert that potential energy into kinetic energy at the bottom of the ramp. Do you understand what I'm saying? At the bottom of the ramp, work was done that equaled the change in kinetic energy. So when dealing with potential energy, like how much potential energy does an object have? Look at my desk. There's a lot of objects on my desk. In fact, consider this for a moment. My coffee cup, perched right there, ever so carefully on the edge of the table. So just to make sure we all have an understanding, there's a table. And my coffee cup, which I love as much as life itself because it has coffee in it, perched precariously at the edge of the table. How much potential energy does it have? The truth is, it's a ridiculous question for a lot of reasons. But the most important, which is, why would I care how much potential energy it has? Is there a reason? Well, it could fall. If it falls, the cup will hit the ground. It will convert this potential energy into kinetic energy. Would you agree that it'll be falling faster if I lift it higher? So how much potential energy does it have? The question I'm trying to explain to you is, well, there is the possibility it could just fall from one tier of my table to another. Right? We all know that my little thing here has more than one tier. So suddenly, do I make this my measurement for potential energy? Is this it? Or is this it? Which one of those is the proper way of measuring potential energy? Which H0 should I use? I mean, I want you to think of it this way. Eventually, I did work starting from the ground outside to bring this cup into the room. Would I have to measure the potential energy relative to the ground outside? Do you understand what I mean when I say that when we talk about potential energy, we could continuously talk about where is the reference level. Problems involving potential energy generally require that we have an agreed upon reference level. Something that makes sense. If we're going to use this, like if I want to figure out how fast the coffee cup's going, if it falls off my desk, it probably makes sense to know where is it going to fall. That's the only time it makes sense. If it falls off my desk right now, is it going to hit the ground outside? No, so I probably wouldn't use that as a measurement of where my reference level is. But if I perched it right here, I would probably be concerned. It could fall to the floor. I'd probably make the floor the reference level. Now, if you're having difficulty grasping why I'm making this a point, consider the problem I will likely have you do. Oof, that's ugly. That's uglier. That's better. Let's say I have a little roller coaster where the top of the first hill is 3 meters high and the diameter of this loop is 2 meters high. And I put a little roller coaster car right there at the top. Now, I want you to pay attention to this because I'm going to try and derive something for you, okay? Let's say the roller coaster car goes here to the bottom. Everybody good? Following so far? I do work to lift the roller coaster car up to the top of the ramp. And we know that that work is going to change the potential energy of the roller coaster cars. We also know that work is going to be done by gravity to bring the roller coaster cars from here to the ground. And we saw, when we did this with the ramp, that this amount of work ended up being equal to this amount of work. Follow so far? Everybody okay with what I've said so far? All right. So, this amount of work caused a change in kinetic energy. So when the cars got down here, they had some kinetic energy. But it was the same amount of work. The work I did, which was against gravity, ended up being the same as the work done by gravity. Now, this part, follow along close. If those were the same, then that had to be the same. If those are the same, then that means negative U final minus U initial has to be equal to K final minus K initial. Now, I'm going to distribute that negative sign. That makes it U initial minus U final equals K final minus K initial. We good so far? Guess not everybody's trying to look over there and read it, so how about I just move it over there? I'm gonna get all the finals on one side and all the initials on one side. So U initial plus K initial equals U final plus K final. This is why potential energy has been defined. Because in a system that's experiencing only a conservative force, energy is a conserved quantity. And say that again, because you don't see the implications of this, and I want you to. In a system experiencing only a conservative force, energy is a conserved quantity. Energy conservation is one of the most powerful ideas in physics. It's incredibly powerful. But if we look at what it does, it says that if you add up all the energy a system has before something happens, it has to equal all of the energy for all time. The energy in a system is conserved. The word here, conserved, means doesn't change or stays the same. That's what conserves mean. Conservative laws are about things that don't change. So in the case of this problem, the energy before equals the energy after. So since gravity is the only force acting on the roller coaster car, when the roller coaster is at the top, if I combine its potential energy with its kinetic energy at the top, it would have to equal its potential energy plus its kinetic energy at the bottom. Well, mg times 3 plus 1/2 m0 squared at the top. I'm assuming we can all agree that this makes a pretty good reference level, which means mg times 0 plus 1/2 mv squared at the bottom. Not calculating work, I'm not talking about force. I just add all the energies from one part of the problem and set it equal to the energy at the other part of the problem. And suddenly, I'll notice first, I don't even have to know how much mass there is for the cars. V has to equal square root of 60. I'm just doing the algebra ahead of time, but do you see why? 3 times g is 30, times the 2 from the 1/2. Never calculating force, never calculating work, never calculating acceleration, just setting something at the beginning equal to the end. And notice, I don't even have to know what the shape of the curve is. It's path independent. This is a curved path. We never could have done that before. How about this? At some point or another, the cars will be here. Same amount of energy. mg times 2 plus 1/2 mv loop squared. Follow what I'm doing? Conservation of energy is very powerful. This is why we define potential energy, to use for this purpose. All forms of potential energy do this. All right. Tomorrow we'll finish